Hi, I'm Jeff Clarkson. In May of 2023, I was asked to lead a project team to develop a new part on assessment of fiber reinforced polymer, or FRP, equipment for API 579. In April of 2024, I provided a live online seminar to members of the API 579 Fitness for Service Code Committee to provide education on FRP. The session covered material on design using FRP, damage mechanisms experienced by in-service equipment, detection of damage, an overview of repairs and monitoring the equipment, and the contents planned for a part in API 579 to assess the fitness for service of FRP. The live session is being recorded here to be available as an ongoing resource for the API 579 committee. Since the initial session, some questions have actually been raised that provide an opportunity to add some additional explanation. As well, some of those slides, we've tried to address all of those questions with new slides in this presentation and in these videos. This video is the first of 4 that are organized as follows: design, damage mechanisms, detecting damage, remediation, mitigation, monitoring, and then basic contents of the FRP part in API 579. The agenda for this presentation, the agenda for all of the videos actually is shown here. Where video 1, this one, regards introduction to FRP, in particular design of equipment. Then video 2 is for FRP damage mechanisms. Video 3 for non-destructive evaluation to detect FRP damage. Video 4, remediation, mitigation, and monitoring, and also a summary of the FRP part for API 579-1 ASME FFS-1. The key items that we're going to cover in this session, in this video, are talk about applications and fabrication methods, discuss and describe several design approaches, describe how tensile properties are different from bending properties, and emphasize and show that only new material properties are used for design. We introduce viscoelastic behavior of FRP materials, and we start with an example that carries throughout throughout the life of all 4 videos. Fiber reinforced polymer is an engineered material of 2 main constituents: a polymer, which is also known pretty widely as the resin, and the reinforcement. Glass fiber, most common. There is increasing use of carbon fiber, partly because its cost keeps coming down, and then some other reinforcement fibers have also been used. It has been in industrial use since the 1950s. So by comparison to steel, which is 1,000 years old, and concrete, which is fully 2,000 years old, this has only been in use for about 75 years. It's a baby of the materials. It is usable up to about 150 degrees Celsius. That actually is highly dependent on the polymer or the resin that was used to make the FRP. Most of the time, the limit is 82 degrees C. And it is equal or superior in corrosion performance to many stainless steel or nickel alloys. The only thing that is really significantly different, especially in acidic applications, is the temperature. If the temperatures are too high for FRP, you have to resort to some of those materials. I'm going to discuss a little bit polymer types. Polymers are an extremely broad field. We really break it into 2 components, 2 types of components. The thermosetting polymer. Some examples are epoxy, epoxy vinyl ester, polyester, and polyurethane. And the important features are these polymers do not melt. You cannot thermoform them. You will never get these out of an injection molding machine. The polymer molecules themselves are cross-linked together to form a relatively rigid and relatively brittle structure. They're currently used for most FRP industrial applications. It is a relatively strong polymer. This session and this video discusses really only thermosetting polymer. Thermoplastic polymers, on the other hand, are things like fluoropolymers or PVC, polyvinyl chloride, HDPE, which is high density polyethylene, polypropylene, and so on. These are fusible. They can be welded, they can be thermoformed. It has modest usage in FRP, and in fact, where it is used is normally for a lining material where superior chemical resistance can be obtained without having to build the entire vessel out of a relatively weak material compared to FRP. A lot of the material in this session, as well as throughout all of the videos, is WRC 601, which is the Welding Research Council Bulletin 601. This provides a lot more detailed discussion of the material, and it provides the technical basis for FRP assessment to be included in API 579. Back to, while we continue, that WRC 601 bulletin, we kept finding opportunities to make it clearer and more practical. So it's right now, it's been updated 3 times now, or twice now. So it's in its 3rd edition. Some applications of FRP, and in fact, fairly broad look here from an industrial perspective. We have piping in this slide, fairly conventional storage tank with, in fact, an atmospheric overflow. This is ducting. These, in fact, are expansion joints made out of FRP. This is a pressure vessel for reverse osmosis purification of water, industrial scrubbing and ducting equipment. These are a set of industrial reactors. And this is a high pressure storage tank, typically made for, I think this is typically made for hydrogen in this application, which works at very close to 15,000 PSI. That's this one here. This is a fabricated material. It comes as a series of ingredients or constituents, and they are mixed during manufacturing. The polymer starts as a liquid resin, so which cures to a solid. A catalyst of some form has to be added. Sometimes temperature has to be added to cure it. And reinforcement comes in a variety of forms. They are mixed at fabrication. Here we're showing 2 examples where they're mixed at fabrication. In both cases, the mixing takes place with the equivalent of a paint roller, essentially squeezing or forcing the polymer, the resin, not the polymer, the resin into the fibers of the reinforcement. Thermoset resins require mixing and curing. So we start with a bulk polymer or bulk resin. We add a catalyst, mix it. Now we have a liquid that is ready to cure. And in fact, for room temperature cure components, the curing starts relatively soon after the catalyst is added. Sometimes they add inhibitors and chemicals to slow it down a little bit. But once the cure is initiated, you have a limited period of time to mix it with reinforcement before it forms a cross-linked solid. This normally has, without reinforcement, this has isotropic properties. So essentially, This is a material that has the same properties in all directions. Glass fiber reinforcements come in a broad variety of styles, but essentially they all consist of individual fibers of glass pulled from a bushing on the discharge of a glass furnace. Normally, a glass fiber is about 13 microns in diameter, so it's about a fifth the diameter of a human hair. Here we show some tows or collections of fibers together, spooled onto or rolled onto a spool. We also see where tows have been woven into different fabrics. And here we have some loose fibers, which in fact have been chopped from tows. All of these are used in some form in most FRP equipment. Glass and the resin don't normally bond together very well, and so to allow that to happen, sizing, which serves the role as a primer, is applied at fiber formation to allow bonding with the polymer. That sizing is also required for the use of any carbon fibers. They also don't bond to the resin before curing. Polymer and reinforcement mixture, once it's finished, we actually get to look at the design basis. The polymer is isotropic and it's cross-linked throughout the FRP. You may have different amounts of cross-linking at different sizes for different layers, but the layers are all typically bonded and linked because there will be bonding sites available on relatively newly formed and newly bonded and newly cured polymer. The other design basis is that layers are fully bonded to their neighbors. Reinforcement is fully bonded to the polymer, and loading is transferred to the reinforcement principal directions. Remember, they're long, slender fibers. Even though glass is an isotropic material, we're really only setting it up to be usable in one direction. And loading is transferred to those principal directions through the polymer via shear. FRP must be formed into the finished shape during fabrication and before the resin is cured. After that, it's no longer formable. So the formation is on molds, and this is essential for the orientation of reinforcement, bonding of polymer to reinforcement, and minimal polymer damage in the finished component. Several fabrication methods are available. Contact molding, I've really grouped two things into this. One is what's called hand layup on an open mold, where in fact the saturated reinforcement is applied to the surface of the mold and rolled in place with rollers, as I showed a couple of slides ago. And another one is a closed mold resin transfer, where the reinforcement, which is here, you can see the glass area or the white area is typically glass that doesn't have resin in it yet. That has been placed into a mold in the orientations required at the final, in the final part. The mold has been sealed and we're now drawing the resin in. This is actually a vacuum infusion process where the resin is coming in from the outer surfaces and it's being drawn in by pulling a vacuum up in this center tube, and so there's actually a wave front of liquid resin moving through the material to get there. Another method, this one is usually much faster in production rate than hand layup, is filament winding, where in fact we collect together a number of strands of of glass. This is from those things like the spools that I showed a few slides ago. We collect them together and then take that through a bath of catalyzed resin and apply it onto a rotating mold. This mold is rotating so that it's drawing these fibers away into the other side of the cylinder. This can be used to provide fairly significantly stronger FRP, and as well we can change the rate at which this carriage travels in order to alter the helix angle, which can give strength properties in different directions. This is another example. This is on a cylinder with a vertical axis, and all of the glass is stationary down here, but in fact what's actually happening is that the cylinder is being rotated against this or relative to this stationary point that is applying the glass fibers onto the cylinder. And this is an example of a continuous winding operation where the mold actually moves and translates the pipe in the axial direction. So the pipe is rotating and translating in this direction so that all of the materials are applied in one place. And by the time it gets past this area that's lighted, it's basically cured and ready to go. Joining thermosetting polymers requires adhesive. You cannot weld this material because we don't have a melting point. So attachments and components are usually joined using adhesive bonds. Here's an example of somebody joining a nozzle into a process vessel. Also for joining, you can use bolted joints. Flanges and anchors and some structural connections use bolted joints. These require a little bit more design finesse because you end up with off-axis loading and bending moments that you have to contend with. For industrial corrosion-resistant applications, the industry and people around the world have basically come up with a fairly standardized construction where the structural layers, which carry most of the load, and in fact design practices normally only consider the effect of loads on structural layers, have got an engineered combination of reinforcement for reinforcement direction and orientation, and polymer addition, so that they have a specific set of mechanical properties, and what's called a corrosion barrier, which is essentially a coating. Now it's a fairly thick coating. This nominally a corrosion barrier is about 2.5 millimeters, 2.4 millimeters thick. And it's a couple of layers of chopped strand glass that chops, and another thin layer of high resin concentration. The corrosion barrier for many codes and standards is omitted from construction calculations. Okay? Now, the corrosion barrier has 85% to 100% by volume polymer. It's very similar to a coating. The structural layers will have from 43% to 80% polymer. Now 43% polymer means that, of course, you've got 57% reinforcement by volume in the FRP. That's a very, very high strength system, and they're also relatively uncommon because they're fairly difficult to make. There are over 200 codes and standards available from ASME or ASTM or API or ISO and some others for FRP materials. Most design methods use an allowable stress design method, and a prescribed factor of safety applied to tensile strength. Sometimes allowable strain limits are used with essentially the same effect as allowable stress design. Now, piping in some pressure vessels often use pressure rating or a long-term hydrostatic design basis, plus allowable stress design where we don't have a basis for the long-term hydrostatic design. Some typical codes and standards that are in use for construction codes, we consider often ASME RTP1, ASME Boiler and Pressure Vessel Code Section 10, EN 13121, and actually that's an ISO standard that I think is used for as many or more vessels than the ASME standards are used for. ASME B31.1 and B31.3 are the most common piping codes. ASME NM.2 is a relatively new introduction piping code, but it's very good. And ISO 14692 for pressure piping. Construction standards include API 12P, ASTM D3299, and ASTM D4097. Many of these standards have significant common ground. So if something is designed to any of these, they're likely to be relatively equivalent. Allowable stress design treats FRP as a linear elastic material. Some example methods, for instance, the allowable stress is equal to the tensile strength divided by the factor of safety. So all you need to know is the tensile strength and the factor of safety, and you can do a stress-based design. Sometimes tensile strength is determined from destructive tests of the samples of the FRP to be used. In fact, in this case, tensile strength is determined that way. There is no yield for this equipment. It only fails in essentially a brittle failure. For ASME RTP1 and ASME Boiler and Pressure Vessel Code Section 10, and this is for something called a Class 2 pressure vessel, where it's designed as a one-off type of vessel. The factor of safety is normally 10 for continuous loads and 5 for occasional loads, such as, say, seismic loads or wind loads, and external pressure as well. Tensile testing is required for some standards. Boiler and Pressure Vessel Code Section 10 requires tensile strength testing for at least examples of the FRP to be used in construction. It measures the strength in one direction of the FRP, so if strength in several directions is important, you have to have test results for each direction. That's important. The reinforcement and the polymer behaves as a mixture. The reinforcement provides 87% to 97% of the tensile strength. The polymer then normally provides 3% to 13% of the tensile strength. So the polymer really doesn't provide a significant amount of the strength that's used in design. ASTM D638 is a standard method that's used for a lot of tensile strength testing. There are some other standards that can be applied for thicker segments or thicker laminates, but they all are essentially the same or very similar. Sometimes you can use short-term pipe cylinder burst for hoop tensile strength. You pressurize a pipe cylinder with closed ends and do it very quickly to determine what that hoop tensile strength is. An example of what a tensile test looks like is shown here, and I've got 3 static examples listed out of here. At the start, of course, there's no damage. And this is from a video that's available online. This is from carbon fiber reinforced polymer. And you can't actually see the carbon fibers within here. You can see a couple of fibers on the outer layers, and they're not the same. They're not continuous like within. As the load starts, you can see that the polymer cracking starts in the outer surfaces here. And that's because the strain in the polymer and the volume of the polymer is such that we start to see the cracking form here. But we're not really seeing too much cracking occur in the middle. And now at this stage, you can see that the polymer is cracked throughout the thickness. And in fact, there's significant cracking, including some cracks across in the transverse direction. The reinforcement is intact. This is not at strength yet. Potentially, there could be an argument made that this is not fit for service any longer because now we have cracked materials within it. An alternate method to determine the allowable stress is allowed in some standards. RTP1 is one that allows it, as well EN 13121, where allowable stress is equal to the calculated Young's modulus times the allowable strain. And we'll cover calculating the Young's modulus later, because if you can't determine the tensile strength for some reason, and it could be because you can't get a sample of the material, you can calculate and provide a modeled version of the Young's modulus, and of course determine what the allowable strain is. An allowable strain is typically the minimum constituent strain at failure, and by the way, this is normally the polymer that has the lowest strain at failure. Surprisingly, it's not the glass, but it's usually the polymer when they're new, divided by the factor of safety. Or, in fact, some standards may stipulate the allowable strain. And in fact, in the example, we have both RTP1 and EN 13121 both have sections where they do stipulate the allowable strain value. So remember, I promised I'd talk about how you can determine Young's modulus without tensile testing. Well, we can estimate it from the FRP construction. And I'm going to use a very brief example for a single layer. In this layer, we have glass reinforcement, which is 33% by volume, which is 53% by mass. This is a relatively, it's sort of a modest or a moderate strength for an FRP layer. This glass, notice the glass fibers are only going in one direction, so they're not contributing directly to strength in the transverse direction. They're contributing directly to strength in the one direction. The principal axis for this layer, the reinforcement's going in the one direction here, and transverse is the two direction. Now the equipment that this is going into is actually oriented where the principal directions of the equipment are X and Y, which are rotated at some angle away from the other axes. There's a single reinforcement orientation per layer, as I mentioned. This method is actually allowed in RTP1, EN 13121, ASME NM-2. It's also allowed in ASME boiler or pressure vessel code section 10, but it's a little more limited in the pressure vessel code. We can calculate the Young's modulus, and in fact, NASA figured this stuff out back in the 1960s, and And you can also get these same calculations in the mill handbook or in RTP1 or in boiler and pressure vessel section, or the boiler and pressure vessel code section 10. Essentially, along the reinforcement axis, remember the axis is 1, we get a calculation which is based on the modulus of the glass and the modulus of the polymer and their relative volume fractions. And then we get a function of those volume fractions, the volume fraction of the reinforcement, the Poisson's ratios, the shear modulus, and again, the moduli of the glass and the polymer. You get a value on the order of 18.87 gigapascals, or 18.64 plus this relatively small contribution. You can see that in fact you can make a pretty decent estimate by taking a look at only the first section. In the x direction, so now we have to rotate it, we actually can use a linear transformation to determine that the modulus of elasticity in the x direction is 8 gigapascals. This method is known as classical lamination theory, and it's actually pretty cool. It will exercise your matrix multiplication. If we have existing FRP, we have no information on how it's made, but we need to know how it was made. We can get that information from a specimen or a cutout. So we get a cutout of a particular size and we can remove the polymer. In the case of glass reinforced polymers, it's very easy. We basically put it in an oven and heat it to burn the polymer out. And that allows us, with weight measurements before and after, to determine the weight fraction of inorganic reinforcement and polymer. If you add organic reinforcements, this can be a problem because they'll burn away. But for glass, it's great. So here's an example of a piece that has gone through the ignition burnout stage, and we actually can separate it away typically by layers, because each fabric is retained or keeps itself within the layers. So we can take these layers and determine what they are, what their orientation is relative to a known axis of the specimen, and reconstruct this, all of this, to give values using classical lamination theory. It can be painstaking work. It's great work for junior engineers. Methods for classical lamination theory can be found in ASME RTP1, the Boiler and Pressure Vessel Code Section 10, Mill Handbook 17, and they're all based on NASA RP 1351, the basic mechanics of laminated composite plates. This work has been in use fairly consistently since the 1960s. What happens with a ply stack, as I show in this image here, is that we can assemble a matrix representation relating loads and moments to the strains, measured or actual strains, and rotations that occur by developing these coefficients. And in fact, I develop on the next two slides A11 and D11. That's why they're circled. This slide shows how to develop the coefficient relating strain to load in the for the 1-1 coefficient in the one direction. And what we do is, for the laminate stack from ply 1 to ply n, each ply we develop a stiffness Q11, which I showed on earlier slides, and that is equal to the Young's modulus in the one direction times 1 minus the square of the Poisson's ratio, which of course is different in each direction, so we use both of them. What happens then is that we are able to sum these stiffnesses. All of these are coordinated or aligned to the same coordinates, all layers. And we then sum them and weight them by their thickness. So for example, this one really shows, for example, for ply K here, it actually for ply K, it becomes the thickness of ply K times the stiffness of ply K, and then adds to all of the other plies. This slide shows how the bending stiffness is developed, and it works quite differently because in fact it's influenced by the distance of by the distance of the layer from the midplane, and as well by the cube of the thickness. And that's because we're dealing with a moment of inertia function when it comes to bending. So therefore the sum is different. It's still essentially the sum of the stiffness of layer K, but the influence of the thickness is magnified by the fact that we're dealing with two things. We're dealing with a moment of inertia and the parallel axis theorem. Classical lamination theory is used in some ways to give some strength information when we deal with failure strain. So we can actually look at strength and failure strain for each layer. Think about that. We have slightly different materials in each layer or slightly different combinations. We can determine what the strength and failure strain is for each of those constituents and look at each layer and determine that from testing. We actually do that in the Boiler and Pressure Vessel Code section 10. When test data is not available, strain limits can actually be applied in RTP1. These limits are set to be conservative. They're actually stipulated in the code, and they're based on undamaged materials. Okay? The strength is equal to the tensile Young's modulus times the strain limit, which is essentially second year engineering mechanics of materials. The Young's modulus, as I've mentioned several times before, depends on direction. The compression modulus is often similar to the tensile modulus. And the tensile Young's modulus is dominated by reinforcement. That actually shows up. Remember, I mentioned that reinforcement generally provides, glass reinforcement generally provides 87% to 97% of the tensile modulus and the tensile strength of FRP. The bending Young's modulus, this is for instance what you would determine with a 3-point bend test, also known as the flexural modulus, depends highly on the polymer and the distribution of reinforcement. There may be some similarities when equipment is new, and as we'll talk about in the damage mechanisms section, there are changes that occur to the flexural modulus that don't occur to the same extent in the tensile modulus. In fact, for an example, FRP construction, this is the same construction, tensile modulus of a particular construction of FRP determined using ASTM D638 is nominally 1.5 million psi. That works out to about 10 GPa. The flexural Young's modulus of the same construction under the same conditions, determined using a 3-point bend test in ASTM D790, is about 1 million psi, and that's somewhere on the order of 700,000 or 7 GPa, not 700,000, sorry, 7 GPa. Layer properties can actually have some effect. So a typical FRP construction will often have the same polymer throughout the thickness. The tensile modulus would be, say, 1255 KSI. The flexural modulus, about 3/4 of that, has 900 KSI. Now, layers 1, 2, and 3 are the corrosion barrier from, as we showed before in this example. And let's substitute polymer in here with one with a lower elastic modulus, say 40% of the other. Now, because this is also probably about 85% polymer, it makes very, very little, if any, contribution to the tensile modulus. So the tensile modulus is going to be about the same. And it is. It's 92% of the original one. But the flexural modulus is reduced to 83% of the original one. So you can see the effect, the beginnings of the effect of the polymer. A Poisson's ratio is also available. It's available for new constituent materials. We can determine it for layers using classical lamination theory, and that's by layer, and for bulk. It's also different for each axis, direction, or order. If we're using classical lamination theory, we can actually perform allowable stress design for each layer. So we can evaluate each layer individually to determine the factor of safety associated with that layer. So we may have layers that are weaker or stronger than others, and layers that will experience failure or cracking before others. We can determine that in this case. We determine in this case the factor of safety is actually the solution of a quadratic equation where H and G are functions of the applied stress over the strength. To see the full development of that equation, that's where you get to read the NASA RP 1251 document. But for this, you have to know the layer details. You cannot guess at this, and you can't get this by looking at a bulk piece of FRP. For allowable strain design, we actually have the same quadratic function, just slightly different A and B, or slightly different values for A and B rather than H and G, and their functions the applied strain over the measured failure strain for the layer in tensile and compression. We also have standardized values available for allowable stress design. These are available for a small number of FRP materials. These are provided in ASME RTP1, ASME NM.3.3. This is essentially the appendix for NM.2 for piping design. So this is non-metallic piping code materials properties. There are some ASTM standards that have a limited amount, similar amount actually to RTP1. And EN 13121 also provides some information on allowable stresses or allowable loads that can be used in the absence of test data. The values that are used and provided in these documents are usually the 2.3rd percentile, which is basically 2 standard deviations less than the average. So you can see we use an allowable stress design of this, even though the average of the test results is up here. And of course, potentially you could have 97th percentile up a fair lot higher. So this provides conservative value that can be used. Accurate FRP strength values are sometimes a little elusive. The strength of FRP in a structure can vary widely. The standards use conservative approaches that make sure that the strength is not overstated. However, there can still be pretty wide variation. So post-construction use of design strength or of original strength is not always reliable. For allowable stress design, most design models FRP as an orthotropic material with different modulus and allowable stress in each of X, Y, and Z directions. And in fact, in these cases, it's actually reasonable to use stress formula for isotropic materials in plane stress. Methods and factor of safety values really allow design to be similar to metal alloys in these cases. So once we know what we're dealing with, it's not too hard to move to the next stage of the design. If we're going to use layer properties, individual layer properties, we assume that all layers are fully bonded to their neighbors. Each layer is analyzed based on its construction and orientation and location in the FRP. You could provide optimized thickness and construction with this. Literally, we could say, no, let's take that layer out. Let's change that. Let's adjust this. And it uses criteria other than allowable stress. Normally, it works on the strain limit method that I discussed above, using the quadratic solution for each layer. Finite element analysis can be a little bit of a challenge with FRP. The reason is that at the minimum, the material must be modeled as linear, elastic, orthotropic bulk materials. The mixture of the polymer and the reinforcement is modeled as a homogeneous material. Now, some FEA software allows FRP to be modeled using layer properties. And by the way, classical lamination theory, which I talked about, essentially reduces each layer to a homogeneous material. The criteria are often similar to design using layer properties, where we can look at individual layers in those cases and solve for strain in individual layers. Load and resistance factor design is not often used for pressure equipment, for example, but there are standards available for the FRP elements of bridge design or other structures, cooling towers, for example. It generally ignores the polymer completely. And in fact, it only looks at strength, tensile strength of the material. It's conservative. It takes the 5th percentile of the strength data and applies a resistance factor of between, say, 0.25 and 0.65. In some cases, it generally does not accommodate chemical environments, so it's really only looking at mechanical loads and mechanical stresses. There are ways to adjust that resistance factor for chemical environments. And in fact, EN 13121 kind of uses an analogous method for design that starts to work almost like a load and resistance factor design for industrial equipment. The long-term hydrostatic design basis is fairly unique to FRP materials. It's used for FRP piping and some prototype pressure vessels. For example, the reverse osmosis vessel that I pointed out earlier is actually certified using long-term hydrostatic design basis principles. FRP is a non-linear viscoelastic material. Its mechanical properties change as a consequence of exposure to stress and strain and chemical exposure over time. Mechanical properties are usually altered by the operating conditions, like I said. Procedures for determining the long-term hydrostatic design basis are available in ASTM D2992, which involves exposing sections of FRP pipe to various pressures for various periods of time. And Boiler and Pressure Vessel Code Section 10 has some discussion of it. The basis is you pressurize equipment to failure, and you determine the pressure that it was under for the various times to failure. So we actually record this on a log plot, so to get a straight line. And this is pretty decent data. This is real data from a customer, or rather from a manufacturer. And in fact, in order to come up with the design basis for a particular time, you find what time that is, or the logarithm of the required time, find this curve, plot back, and you can say that is the maximum pressure that it should be exposed to for that. This is very specific for a single design set of materials and construction. And for pressure vessels, we actually govern this or cover this in part RT 220 of Section 10 of the Boiler and Pressure Vessel Code. We run pressure cycles for 100,000 cycles to the design pressure. Then we pressure test it, and it has to reach at least 6 times the design pressure before it fails. And the rating is the maximum pressure reached before it fails. So potentially the rating is higher. Usually you should expect the rating to be higher than the design pressure. Reverse osmosis vessel, hydrogen storage vessel. When we're using the long-term hydrostatic design basis, we're using performance data for a specific construction. It's actually widely used in piping design codes, ASME B31, ASME NM.2, and ISO 14692. Within those codes, you can also design design using calculations and stress analysis, but this method is easily there, and it allows manufacturers, in fact, to qualify specific pipe designs for pressure environments. This is not used for fittings, flanges, vessels, or other structures. The hydrostatic design basis is combined with allowable stress design when we start getting into, when we start to have to consider supports or joints or fittings or some other items in design which are not directly related to internal pressure. Non-destructive evaluation, it has very limited use in FRP construction codes. Visual inspection is used. This is the most extensive inspection used, where people or inspectors are required to look for specifically visible features that may or may not affect the acceptance of equipment by the code. Hardness of the surface is taken using a durometer impressor. It's called a Barcol impressor. ASTM D2583 covers that. Acoustic emission testing is used in RTP1 in the Boiler and Pressure Vessel Code Section 10. It's also included or covered in standard ASTM E1067, and it's also included in Boiler and Pressure Vessel Code Section 5. There are thickness options. You can use a micrometer, which of course requires two-sided access. A digital magnetic intensity instrument, where if a magnetic material can be placed on one side of the FRP, we can determine how thick it is, the length of the or the distance away that it is. Or an ultrasonic thickness gauge. And RTP1 has a limitation saying that if it's found to be accurate, Section 10 doesn't get nearly as concerned about that. An overview of what we've covered now when we discuss the design. That existing standards and codes provide reliable FRP industrial equipment. They really do. We are dealing with equipment. I have personal experience with equipment that is currently 67 years old. Different design methods can be used with similar results and reliability. It's important to note that Young's modulus in bending is quite different from tension. And construction codes and standards are based entirely on properties measured for new FRP. And they don't provide guidance on damage or fitness for service assessment. Now we're going to talk a little bit about an example. This is based on some equipment that we have some direct experience with. So we're giving an example from the real world. It's a scrubber sump. Inside diameter is 4.27 meters. The length to the rigid stiffener is 4.27 meters. There's an external pressure of 3 kPa, and that external pressure is typically a stack effect. We've got a vertical outlet here. The liquid-specific gravity when there's liquid in the sump is 1.3. The overflow height is 900 millimeters, somewhere around here. So we don't have that much liquid height in the equipment. Temperature is 82 degrees Celsius, so it's within a safe range for virtually any polymer. The construction code is ASME RTP1. FRP construction, in RTP1 there are 2 types of FRP listed. There's type 1 and type 2. This is type 2, which is a slightly higher strength. And in fact, table 2A-1 gives the mechanical properties for it. And the factor of safety for internal pressure, 10. For external pressure, 5. When we do the calculations, the first thing I'll do is I'll pull up the table from RTP1 that gives the material properties. So this is table 2A-3, the minimum values of flat laminates. And you can see we actually have a couple of things in here. Remember I told you we have type 1. All thicknesses of type 1 have the same properties. And if you look down this table, you'll see that those properties are all less than the properties of any of the type 2. On the type 2, type 1 has no unidirectional fibers in it. The type 2 has varying degrees of unidirectional fibers. And in fact, we have type 2 of particular thickness, and you can see that these values increase a bit as the thickness increases. Okay. Notice that I've got the ultimate tensile strength, the tensile modulus, the ultimate flexural strength. This is something that we haven't discussed in this module so far, and frankly, we're not going to need to talk about it. And the flexural modulus, which is, notice, about 70% of the tensile modulus. Now, type 2 actually includes corrosion barrier in the ultimate tensile strength values. This allows any calculations this way to be conservative, because we're also including the very weak corrosion barrier layers in part of the strength. So it allows things to be conservative. We went to classical lamination theory to get the Poisson's ratio, because it's not supplied in this table. But if we look at this, we have for the different values of type 2 here, the Poisson's ratio changes slightly, and that's because it's influenced by the relative amount of glass and polymer. Okay, so we have our material properties worked out. When we do the calculations, we know that, and we're inferring that right away, that we're not going to worry too much about the internal pressure, but we're going to run calculations for internal pressure anyway. So when we do that, we get the ultimate tensile strength from table 2A-1, and when we work this out for the thinnest section from 2A-1, we get a value of required thickness of 0.15. We can use the minimum stipulated thickness from the table of 0.22 inches. So we know that it only has to be 0.22 inches thick in order to meet all of the structural requirements for the internal pressure. This is in the bottom section. For external pressure, well, we don't use tensile strength really at all when we calculate what's happening with external pressure. But what we do is we use the tensile Young's modulus, and to a lesser degree the flexural Young's modulus, and remembering that when we start buckling, we're dealing with bending as opposed to tension. So it's appropriate that we should include some flexural Young's modulus in this. We actually have a prescribed equation in RTP1 part 3A, and that prescribed equation is this one, where the thickness is equal to this function, okay, where we have a knockdown factor, diameter, another proportionality constant. Gamma is actually a function of a number of variables, and the fairly high relevance of the flexural modulus raised to the 0.75 compared to the tensile modulus raised to the 0.25. When we get that, to solve this, we have to go through some iteration, because what happens is that essentially the Poisson's ratios, as well as the modulus ratios, change with different thickness values. What we come up with is the solution at the end ends up with 0.634 inches being the required thickness of this section for the external pressure applied. And in fact, the nearest thickness aligned with that from table 2A3 is 0.641 inches. From that, we're able to know what the design is. Now, in fact, this equipment was built almost exactly to that thickness. 16.3 millimeters. We normally are seeing this vessel to be 16.5 to 18 millimeters, and there's Remember I said there's some variation in thickness when they make things because we have a relatively random process, or more randomness in the process, making it with involvement by people with paint rollers. At this point, I'm ending video 1. We've now gone through the basics of design, and we have talked about the principles involved and given an example. Feel free to address any comments or questions to me at the coordinates that I list on this slide, and I'll happily answer them. Thank you very much.